On today's programme, Dallas takes part in a citizen science experiment.
A million-strong army of people like you and me helping change the way we think about our world and beyond.
Dr. Yan calculates the speed of light.
I'm going to use this blender.
And Jem builds a homemade laser.
Let's see what 5,000 volts does to this little arrangement.
That's Bang Goes the Theory, revealing your world with a bang. Hello and welcome to Bang Goes the Theory. We start tonight with lasers. We've just had the 50th anniversary of the invention of this revolutionary form of light. But how exactly do they work? Well, Jem has been finding out.
Lasers were first suggested almost 100 years ago by who else but the grandfather of science, Albert Einstein. He theorized that if a material could absorb light, then under certain conditions, it could release it as well. If that happened, it would create a brand new type of light that simply didn't exist on our planet. But back then, nobody had any idea if a new type of light would be of any use to anybody. Ready for action. Even in 1960, when they built the very first laser, the team did not know what to do with it. One guy said, "This looks like a solution waiting for a problem." It's solved an awful lot of problems since then. It used to be quoted that on average, you're never more than 6 feet from a rat. Now it's estimated you're never more than 8 feet from a laser. They're everywhere. They're in your CD player, your DVD player. They're performing eye surgery. They're treating cancers. They're transporting data across the internet. They're even scanning your weekly shopping. Beep. That's a laser. I mean, what other problems would you want lasers to solve? How about the world energy crisis? Here at the STFC Central Laser Facility near Oxford, they're pointing one of the world's brightest lasers at exactly that problem. Nobody's going to pretend that laser physics is a piece of cake, but the fundamentals are actually quite simple. So how do you make a machine that you can plug into the wall and convert a few minutes of mains electricity into a pulse of light so intense it would make a star look dim? Well, first, you've got to store that electricity. And for that, you need something like a giant battery bank. These fellas. Now, these store about as much energy as a hand grenade. And at the flick of a switch, it's released into a series of flash bulbs. Now, like camera flashes, they're extremely intense, but only on for a very short period. The energy from that blast of light is absorbed by a lump of lasing material. Now, in this case, they're neodymium atoms, the same ones that are used to make powerful little fridge magnets. So now, that energy that we took from the plug socket is stored as a bunch of identically excited atoms poised, ready to re-release it. And the trigger to release it is a little pulse of light. If you think of a beam of light being made up of a stream of little bullets called photons, when one of those photons hits an excited atom, it releases an identical photon. And as these photons cascade through the lasing material, they cause all the atoms to release all their energy. And by the time it comes out of the end, almost instantaneously, you've collected that energy as a pulse of light. At this point, we've got ourselves a pulse of laser light. It's about this long. It's traveling at 186,000 miles a second and could get to the moon in literally a couple of clicks. The laser pulse flies through the building, getting focused and directed by a series of mirrors until it emerges through those windows into this room, where it finally gets directed into here, where a capsule of unsuspecting hydrogen atoms gets such a massive kick they fuse together, releasing energy, the kind of energy that powers our sun. Now, obviously, I couldn't be here if this was switched on, but with the success they've had with the experiments in this facility, there's plans to build a generating station, a laser-powered generating station where the heat from that fusion will boil a fluid, drive a turbine, turn a generator, and create safe, sustainable energy for at least the next 1,000 years. Inspired by that, I feel we've got to have a go at building our own laser.
We still really underestimate how ubiquitous lasers are in the modern world, don't we? The really exciting bit for me is this whole fusion thing. Every time I meet somebody in that field, I always get the impression the technology it's still 20 years away. It's, and a couple of years later, it's 20 years away. What do you feel now that you've seen it firsthand?
I was at the same school of thought as you. I'm like, fusion, yeah, 20 years away, I know that.
Yeah.
But after having been there and speaking to the guys working at the facility, I'm quite heartened, really quite heartened, because they themselves were saying that when they started working on laser-based fusion there, they were very sceptical. But over the years, recent years, they've ticked off one by one the obstacles in the way. And even to the point that they're going through the periodic table, looking at all the elements that they use, going, no, we can't use that element, there's not enough of it. No, we can't. They're genuinely looking for a sustainable energy source for the next 1,000 years. And I think they're close.
Interesting. But in terms of laser fusion and plasma fusion, which is the other way they're trying to achieve the same thing, it's a two-horse race. I kind of feel more of an affinity with the plasma people. Because I visited the Joint European Tourists last
What about you, Jim? So you're more laser, are you?
Plasma.
When I was there, I was very, very impressed with every part of the setup.
We have a divided camp, I love it.
Well, but it's good that there's a bit of rivalry. It's not rivalry, but it's good you've got, because a bit of healthy competition.
Keeps you on your toes, it fast-tracks the research, it's a good thing, yeah.
And the other thing, we're talking of research was for lasers. The thing that's come out of it for me is the blue sky research element of it. When they started on lasers, it had no application at all.
Yeah.
They were just building it for the sake of building it. Yeah. And now they're everywhere. And in science today, there just isn't so much of that blue sky research. And I think it's something we should go back to.
Definitely.
Well, I guess it's economics.
Yeah,
people worry about economics. Question, why do you want to build a laser? When most people think of lasers, we think Death Stars, we think of people being strapped to metal gurneys, that kind of thing.
Why
talk
go
us
there, Jen?
Talk us through the idea.
They're simply amazing. I mean, but hideously dangerous.
Hideously?
Which is why anybody with kind of designs on world domination, first thing to do is build a laser.
Step 1, build a laser.
Step 2, buy a white cat.
OK, moving on. Time for more Dr. Yan. He's actually using a laser in this week's experiments because he's calculating the speed of light.
Now, for centuries, measuring the speed of light was a great scientific challenge. But about 150 years ago, a French bloke called Armand Fizeau managed it using just a light, some lenses, a mirror, and a special sort of wheel. What he did was he sent light through the spokes of this wheel. So it went on, off, as the spokes blocked the light, and that sent pulses of light. Fizeau wanted to measure the time it took for that signal to travel to a distant mirror and back again. Now, ideally, a scientific experiment should be repeatable, and I've always wanted to have a go at this, so time to give it a go, bang style. So I've come to the National Physical Laboratory, where Simon Hall and Richard Stevens are going to lend a hand. Okay. Now, while we're setting up, I'll show you what Fizeau did and what I hope to achieve with my DIY setup. Incredibly, Fizeau's master craftsman made him a disc with 720 slots. Now, all I've done is print one out, but onto a sheet of transparent paper, like this. Let me show you how it worked, but with a disc with fewer slots. So imagine that Fizeau had his light, and it was shining through the slot and bouncing off a mirror over there. Okay? If the disc is going slowly, then by the time the light goes to the mirror and back again, it'll just come through the same slot. But if it's going fast, then it'll zoom over there and come back. By that time, the disc will have turned a bit, and the light will be blocked. Faster still, of course, and the light will go through the next slot in turn. And so, if you know how fast the disc is turning, then we can use that to calculate the speed of light. All it is it's the distance between here and the mirror, and back again, divided by the time it takes for the disc to turn from that to that. Now, Fizeau turned his disc using clockwork. I'm going to use this blender. The instructions say it goes up to 17,000 revolutions per minute. It's pretty fast. Now all we need is some light, and I'm just going to use this laser. We've set up the laser in the NPL Sports Pavilion and pointed it across the fields. Now I need to set up the mirror as far away as possible. Whoa, well that's quite a long way actually, isn't it? That's, I reckon, about 466 metres to there. That's 932 metres, almost a kilometre round trip. So should we put the mirror here?
Oh, it's quite well.
Yeah. There we go, like that. Is that right in the middle then?
It's not bad.
It's not bad, is it? Well, I think that's adjusted just right. This mirror should be sending the beam back in exactly the direction it came out. Now, I really hope this is going to work. There's loads that could go wrong. I don't think anyone's tried doing it with the blender before. Okay, fingers crossed. Excellent. Right. Okay, so here's our setup. We've got a laser here, and it goes through this lens, which sends it all the way down there. And of course, here we have a disc that's in the way. That's the slotted disc that's spinning round, and it's my blender that's making it spin. Now, you can tell how fast it's going by the noise, but I've got this special piece of kit which will allow us to do it. Okay, so this beam of light whizzes off through this hole and way out to that mirror over there. Oh, I can just see the light. That's really cool. Straight back again, and back through this hole, which makes sure that the beam goes through the same spot on the disc there that it went out. And then it comes back again through here, and then it hits the edge of that little mirror there, and we should be able to see when the light starts getting blocked. That should tell us the speed of light. Okay, Simon, do you want to do the speed on the blender? Brilliant. I'll just have a look in here. Brilliant. Okay, start up the blender. Okay, lights off. Now, this is proving really hard to see. Try to ignore the bright red patch on the left. That's not the reflection from the mirror outside. Instead, look at the faint patch on the top right. We're looking for the moment that patch almost disappears.
So speed it up a bit. Bit more, bit more.
Oh, there. Oh, it's hard to see, but the disc's spinning fast enough to block the returning light, just as Fizzo's did. Now all we need to know is how fast it's spinning to calculate the speed of light.
I reckon that's probably about as dim as we're going to get. Okay, that's really cool. Right, lights on. Okay, so how fast do you reckon the disc was switching from on to off?
3.3 microseconds.
3.3 microseconds. That's 3.3 millionths of a second. Right, time to do the calculations. Right, so we know the distance that the light travelled. That's 932 metres. And we know how fast the disc turned from on to off. 3.3 millionths of a second. That's 0.0000033. And that should be the speed of light. 282 million metres per second. 28242. And the real number, well, it's basically almost exactly 300 million metres per second. So we weren't too bad, actually. That's really cool. And Fizzo, amazingly, with much simpler apparatus than this, managed to get within 5% of that value. That's just incredible.
Here's a little nuggety fact for you. You know the guy who discovered the speed of light?
Fizzo.
Fizzo. Do you know what his first names were?
I don't actually know.
Armand Hippolyte. Hippolyte.
Hippolyte.
Hippolyte apparently means charging horse.
It sounds like a sports energy drink or something.
It's good, because you imagine when you're naming your child, you go down the list, get to the H's, and you're like, Harry, Henry, Hippolyte.
Quite.
Hippolyte, it's nice.
Make
Hippolyte.
a note of that.
Yeah, it's good.
Dr. Yan, getting better every week.
That was
Love
a great
that.
film.
Yeah, really. To think you can measure the speed of light, the fastest thing in the universe, using a blender. I love it.
Well, you say it's the fastest thing in the universe. You're actually forgetting one thing.
Hold on, it is the fastest thing, speed of light.
The tachyon. Have you come across tachyons?
No.
Hypothetical subatomic particles which they think may go faster than the speed of light.
So how fast?
Really, really quickly. It's quicker than the quickest thing ever, which is the speed of light. I tell you what, if Dr. Yan finds and measures a tachyon, we'll let him in the studio.
Okay, that's harsh.
Well, I think it's fair. Harsh but fair. Now then, I'm obsessed with science now, but I really struggled with science subjects at school. And unfortunately, a lot of people, when they hear the word science, can recoil in fear and attempted never to think about science again, which is sad when you consider that at its heart, science is about our inherent natural curiosity. Well, that's where citizen science comes in, opening the doors of scientific research and making the adventure available to everybody. Scientists really do need you. Science isn't just for scientists. Perhaps like me, you've got a passion for science, whatever your walk of life. But what if you did want to get more practically involved? What if you want to roll up your sleeves a bit and get stuck in? Then welcome to Citizen Science, a million-strong army of people like you and me doing real science, making genuine discoveries, and helping change the way we think about our world and beyond. Citizen science has been around for a while, but it really kicked off in the 1990s when scientists started using people's home computers to help them analyse data. Since the 90s, citizen science has moved on from just data crunching by harnessing idle computer power. Instead, it's about getting us to observe, to experiment and to record, so less about computer power and more about people power. You see, before scientists can come up with any meaningful conclusions, they might have to make millions of observations. Now, that could take one scientist 50 years, but a crowd of citizens just a few months. It's a no-brainer.
When we get to 10.
You gotta slow down.
Hang on, slow down.
Oh.
Scientists from all disciplines have cottoned onto the power of citizen science. Today, Mark McCarthy from the Open Air Laboratory Network has come to my local park. Morning, everyone. On a recruitment drive for their latest project. Mark, do you want to just explain a little bit about what on earth you're doing with my poor friends and my poor neighbours on this cold, blustery morning?
Absolutely. This is a citizen science project looking at aspects of the atmosphere, how we influence climate and how climate affects us.
Here's my question. Why can't you guys as scientists just do this yourself? Why can't you just turn up today and measure your own bubbles?
We need sampling at a scale that we just can't get from our standard monitoring equipment and the local knowledge that goes along with that.
So what experiments are we going to do today?
Using a mirror and a compass, we track how the clouds are moving across the sky to determine the direction of the wind at the height of the clouds.
So we've got a compass, we've got a mirror, and you basically look down, you find a cloud,
yes.
and then you sort of follow it and see which way it's moving.
Yes.
It's genius. It's fantastic.
And sticking with the theme of winds, but now coming right down, is when we use the bubbles. So this is the other component of the experiment, where we're now using bubbles to track winds at our level.
Fantastic. So we can make comparisons between what the clouds are doing way up there and then what the wind's doing.
Yes,
Fantastic.
And this is important for us because what we don't have are the observations from the spaces and places that people are actually inhabiting. The data that we retrieve from all of the people that contribute in this project will feed into genuine science papers, which can ultimately help us improve the advice that we provide to policymakers.
But it's not all about the weather. There's a citizen science project for everyone. Now, I'm really passionate about space, and even though I've got this niggling doubt that I might not make it as an astronaut, I can still conduct my very own space research and hopefully further our understanding of the universe. That's where a very special project called the Zooniverse comes in. And what better place to find out about it than the Royal Observatory, Greenwich. So, Robert, can you just give me a little bit of background about what the Zooniverse is all about?
Well, the Zooniverse is basically the internet's largest collection of citizen science projects. It started in 2007. It was called Galaxy Zoo, was the original project, and we were getting people to look at images of galaxies from a massive online catalogue called the SDSS. They were to look at the galaxies and decide whether they were elliptical, whether they were blobs, small round blob galaxies, or whether they were spirals, whether they had those beautiful spiral arms. And that was the basic gist of the project. 2 years in, we've done 60 million clicks, and the whole thing has run away with itself.
Why do you need humans rather than computers to look at these images?
Well, computers can do it to a degree, but their error rate is not as good as humans are. So with visual recognition on the Galaxy Zoo project, the computer could get it right 80-something% of the time, whereas people get it into the 90% range.
So I'm potentially better than a computer?
Yes.
Like maybe a ZX81 or something. My challenge as a citizen scientist is to decide whether the spot at the centre of this image reveals a supernova. The first two images are of the same bit of space, but taken at different times. If there is a supernova, there'll be a change in brightness, shown as a bright spot in the third image.
Is there a supernova?
Yes.
And is there a supernova in this one?
No, I'm going to say no. I'm going to say that is not a supernova. Yes.
And do you think there's a supernova in that one?
Yes, definitely. How did I do?
Actually, 100%.
Okay,
well done, you got them all correct.
And so the computer didn't get them all right. The computer would make mistakes.
So the computer thinks that all of these are supernovae. Every single one. And so what you've shown, and this is a very good example, that's clearly, there's nothing going on there. The computer's just made a mistake.
See, that's really interesting because all these pictures, it's not, you know, you don't need a great deal of science. You're really just looking for a bright blob, and if you can see that. And
yeah, so people are able to look at these images and see things that are unusual or interesting, and of course the computer can't do that. So it really does go into contributing to furthering the knowledge of astrophysics.
Dallas, I am thrilled we seem to be returning to the great age of the amateur scientist.
I totally agree. I think it's really important. I think there's, you know, a wider point here, which is that you don't need to have a PhD to be interested, to be passionate about science, and to get involved in science. And that's not to sort of detract from the importance of academia, but it just means that, you know, that fear that people have about science sometimes is starting to recede, I think.
It's a good thing.
Yeah.
It's also interesting to think about people that most people consider to be academics, like Darwin, for example. He was an amateur to start with, you know?
Absolutely, you know, as was Faraday, as was Wallace, as
Gromit.
Exactly, yeah.
Sorry, Dallas.
No, it's fine.
The other thing I love about that film, actually, is the reminder that as much as we really do rely on them in the modern world, sometimes human beings just do the job better than computers will.
No, we absolutely do. You know, the human brain is just very, very good at pattern recognition.
Yeah.
And when it comes to observation, which is the foundation stone of science, you know, we can just do that. You know, the more people you have doing that, the better your observations are going to be, the better the data you're going to get. Long live the amateur scientist.
Now back to my homemade laser. It turns out that without very specialist equipment, making your own laser is not only phenomenally difficult, it's also extremely dangerous. But I still want to make one. With a bit of research, we've stumbled across a 1960s design for a laser that can just about be knocked together from things lying around a workshop. Add some nuts, a string of resistors, a few diodes, and a pad of sticky notes. Now, believe it or not, that might be a laser. I've not switched it on yet because it's very dangerous. I'll talk you through it. The tin foil and plastic is to make a capacitor to store electrical energy. The nuts here are weights to stop the things moving around. This bit here is a kind of switch. When the voltage gets high enough, it rips the air apart between those two, makes a spark, and switches it on. And this little gap here, between those two pieces of aluminium, is where the lasing should take place. The vast laser facility I visited used neodymium atoms to produce the laser. We haven't got any of those. I don't even know where to get them from. So we need a cheaper, easier to get hold of lasing material. And I'm going to try fresh air. About 80% of the air around us is made of nitrogen. And it's the nitrogen in that little air gap there that gets excited by the electricity and is able to hold itself in that excited state long enough that when a photon of light gets released down here somewhere, it stimulates all those nitrogen molecules to release their photons of light. And that comes out as a laser beam. Because it'll be nitrogen doing the lasing, I can predict the kind of laser we'll get. Now, there's a problem with that laser beam. You can't see it very easily. It's an ultraviolet laser, which kind of makes it doubly dangerous because you don't quite know where it is, and it will definitely burn your eyes out. So for that reason, before I switch it on, I'm going to wear these. You only get 2 eyes. It's hard to believe this kit really is going to produce a laser from thin air, even if we do hit it with some frightening voltages. But here goes. Let's see what 5,000 volts does to this little arrangement. Now, That might be working, but we can't see it. If I put this piece of paper here, look at that! That dot is my laser. The white paper fluoresces where it's hit, just like white clothes do under disco lights. Brilliant! But one little spot isn't enough for me. I want to see the whole beam. It's the chemicals in washing powder that make your clothes fluoresce under UV lights. So if I add some to a tank of water, I should be able to reveal the laser beam. There it is, our own homemade laser. Okay, before we go any further, I've just got to say, don't make one of those.
Fair enough.
As much as I want everybody to be as involved in science as possible, not lasers.
Not this bit, not this bit. I'm amazed at how you actually made a laser out of all that junk lying around your workshop. But what were the sticky notes for exactly? I don't understand them.
They were a little nod towards health and safety. You see, the thing is the laser beam can emerge from either end.
Oh, okay.
And the sticky notes just sort of halve the danger.
What would happen if I actually put my hand in front of the UV laser, like...
Just don't. Intense UV light and human skin, not a good combination.
Kind of makes sense. OK, we shall see you next week. Say goodbye, boys.
Bye. Bye.